In statistics, an outlier is an observation point that is distant from other observations. An outlier may be due to variability in the measurement, or it may indicate experimental error. The latter are sometimes excluded from the data set. Outliers can occur by chance in any distribution, but they are often indicative either of measurement error or that the population has a heavy-tailed distribution. In the former case, one wishes to discard them or use statistics that are robust to outliers, while in the latter case they indicate that the distribution has high kurtosis and that one should be very cautious in using tools or intuitions that assume a normal distribution. A frequent cause of outliers is a mixture of two distributions, which may be two distinct subpopulations, or may indicate correct trial versus measurement error. This is modeled by a mixture model. In most larger samplings of data, some data points will be further away from the sample mean than what is deemed reasonable. This can be due to incidental systematic error or flaws in the theory that generated an assumed family of probability distributions, or it may be that some observations are far from the center of the data. Outlier points can therefore indicate faulty data, erroneous procedures, or areas where a certain theory might not be valid. However, in large samples, a small number of outliers is to be expected. Outliers, being the most extreme observations, may include the sample maximum or sample minimum, or both, depending on whether they are extremely high or low. However, the sample maximum and minimum are not always outliers because they may not be unusually far from other observations. Naive interpretation of statistics derived from datasets that include outliers may be misleading. For example, if one is calculating the average temperature of 10 objects in a room, and 9 of them are between 20 and 25 degrees Celsius, but an oven is at 175 degrees Celsius, the median of the data will be between 20 and 25 degrees Celsius, but the mean temperature will be between 35.5 and 40 degrees Celsius. In this case, the median better reflects the temperature of a randomly sampled object than the mean. Naively interpreting the mean as a typical sample, equivalent to the median, is incorrect. As illustrated in this case, outliers may be indicative of data points that belong to a different population than the rest of the sample set. Estimators capable of coping with outliers are said to be robust. The median is a robust statistic, while the mean is not. Occurrence and causes. In the case of normally distributed data, the 3 sigma rule means that roughly 1 in 22 observations will differ by twice the standard deviation or more from the mean, as 1 in 370 will deviate by 3 times the standard deviation for details. In a sample of 1,000 observations, the presence of up to 5 observations deviating from the mean by more than 3 times the standard deviation is within the range of what can be expected, being less than twice the expected number and hence within 1 standard deviation of the expected number (C Poisson distribution), and not indicative of an anomaly. If the sample size is only 100, however, just 3 such outliers are already reason for concern, being more than 11 times the expected number. In general, if the nature of the population distribution is known a priori, it is possible to test if the number of outliers deviate significantly from what can be expected. For a given cutoff of a given distribution, the number of outliers will follow a binomial distribution with parameter p, which can generally be well approximated by the Poisson distribution with I equals Pn. Thus if one takes a normal distribution with cutoff 3 standard deviations from the mean, p is approximately 0.3%, and thus for 1,000 trials one can approximate the number of samples whose deviation exceeds 3 sigmas by a Poisson distribution with I equals 3. Causes. Outliers can have many anomalous causes. A physical apparatus for taking measurements may have suffered a transient malfunction. There may have been an error in data transmission or transcription. Outliers arise due to changes in system behavior, fraudulent behavior, human error, instrument error, or simply through natural deviations in populations. A sample may have been contaminated with elements from outside the population being examined. Alternatively, an outlier could be the result of a flaw in the assumed theory, calling for further investigation by the researcher. Additionally, the pathological appearance of outliers of a certain form appears in a variety of datasets, indicating that the causative mechanism for the data might differ at the extreme end. Identifying outliers. There is no rigid mathematical definition of what constitutes an outlier. Determining whether or not an observation is an outlier is ultimately a subjective exercise. There are various methods of outlier detection. Some are graphical, such as normal probability plots. Others are model-based. Box plots are a hybrid. Model-based methods, which are commonly used for identification, assume that the data are from a normal distribution, and identify observations which are deemed unlikely based on mean and standard deviation, Chauvinet's criterion, Group's test for outliers, Park's criterion. It is proposed to determine in a series of observations the limit of error, beyond which all observations involving so great an error may be rejected, provided there are as many as such observations. The principle upon which it is proposed to solve this problem is that the proposed observations should be rejected when the probability of the system of errors obtained by retaining them is less than that of the system of errors obtained by their rejection multiplied by the probability of making so many, and no more, abnormal observations from A. Manual of Astronomy 558 by Chauvinet. Dixon's Q-test, ASTME 178 standard practice for dealing with outlying observations. Mahalanobis distance and leverage are often used to detect outliers, especially in the development of linear regression models. Other methods flag observations based on measures such as the interquartile range. For example, if under the lower and upper quartiles respectively, then one could define an outlier to be any observation outside the range. For some non-negative constant. Other approaches are distance-based and density-based, and all of them frequently use the distance to the k nearest neighbors to label observations as outliers or non-outliers. Modified Thomson-Tau test. The modified Thomson-Tau test is a method used to determine if outlier exists in a data set. The strength of this method lies in the fact that it takes into account a dataset unregistered trademark S standard deviation, average, and provides a statistically determined rejection zone, thus providing an objective method to determine if a data point is an outlier. How it works: first, a dataset's average is determined. Next, the absolute deviation between each data point and the average are determined. Thirdly, a rejection region is determined using the formula. Where is the critical value from the student t-distribution, n is the sample size, and s is the sample standard deviation. To determine if a value is an outlier, calculate I equals x, mean, x/s. If I rejection region, the data point is an outlier. If I a per-mille currency rejection region, the data point is not an outlier. The modified Thomson-Tau test is used to find one outlier at a time. Meaning, if a data point is found to be an outlier, it is removed from the data set and the test is applied again with a new average and rejection region. This process is continued until no outliers remain in a data set. Some work has also examined outliers for nominal data. In the context of a set of examples in a dataset, instance hardness measures the probability that an instance will be misclassified. Ideally, instance hardness would be calculated by summing over the set of all possible hypotheses. Practically, this formulation is unfeasible as is potentially or infinite, and calculating is unknown for many algorithms. Thus, instance hardness can be approximated using a diverse subset. Where is the hypothesis induced by learning algorithm trained on training set with hyperparameters? Instance hardness provides a continuous value for determining as an instance is an outlier instance. Working with outliers, the choice of how to deal with an outlier should depend on the cause. Retention: even when a normal distribution model is appropriate to the data being analyzed, outliers are expected for large sample sizes and should not automatically be discarded if that is the case. The application should use a classification algorithm that is robust to outliers to model data with naturally occurring outlier points. Exclusion, deletion of outlier data is a controversial practice frowned on by many scientists and science instructors. While mathematical criteria provide an objective and quantitative method for data rejection, they do not make the practice more scientifically or methodologically sound, especially in small sets or where a normal distribution cannot be assumed. Rejection of outliers is more acceptable in areas of practice where the underlying model of the process being measured and the usual distribution of measurement error are confidently known. An outlier resulting from an instrument reading error may be excluded, but it is desirable that the reading is at least verified. In regression problems, an alternative approach may be to only exclude points which exhibit a large degree of influence on the parameters, using a measure such as Cook's distance. If a data point is excluded from the data analysis, this should be clearly stated on any subsequent report. Non-normal distributions, the possibility should be considered that the underlying distribution of the data is not approximately normal, having fat tails. For instance, when sampling from a Cauchy distribution, the sample variance increases with the sample size, the sample mean fails to converge as the sample size increases, and outliers are expected at far larger rates than for a normal distribution. Set membership uncertainties. A set membership approach considers that the uncertainty corresponding to the if measurement of an unknown random vector x is represented by a set xi. If no outliers occur, x should belong to the intersection of all xi's. When outliers occur, this intersection could be empty, and we should relax a small number of the set xi in order to avoid any inconsistency. This can be done using the notion of Q-relaxed intersection. As illustrated by the figure, the Q-relaxed intersection corresponds to the set of all x which belong to all sets except Q of them. Sets xi that do not intersect the Q-relaxed intersection could be suspected to be outliers. Alternative models. In cases where the cause of the outliers is known, it may be possible to incorporate this effect into the model structure, for example by using a hierarchical Bayes model or a mixture model. See also, anomaly detection, anomaly time series, robust statistics, robust regression, box plot, King effect, studentized residual, Winsorizing, data transformation, local outlier factor, references. ISO 16269-4, Statistical Interpretation of Data Part 4. Detection and Treatment of Outliers, Struts, Tylo. Data Fitting and Uncertainty, A Practical Introduction to Weighted Least Squares and Beyond. Vierg plus Tubner. ISBN A978-3-8348-1022-9. External links, Renz, John, Outlier, MathWorld. Balakrishnan, N. Childs, A. Outlier, in Haswinkel, Mikhail, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Grubbs test described by NIST Manual, How to Detect Univariate Outliers, How to Detect Multivariate Outliers and How to Deal with Outliers.